What's up, everybody? This is Healing Intentions, and I'm your host, Dr. Adrian Mehmedi. This podcast is about natural health and wellness, mental health, cannabis, psychedelics, philosophy, and spirituality. Today, my guest is Dr. Gerald Pollack. Dr. Gerald Pollack received his PhD in biomedical engineering from the University of Pennsylvania in 1968. He then joined the University of Washington faculty and is now professor of bioengineering. He is also founding editor-in-chief of the journal Water, convener of the annual conference on the physics, chemistry, and biology of water, and executive director of the Institute for Venture Science. His interests have ranged broadly from biological motion and cell biology to the interaction of biological surfaces with aqueous solutions. His 1990 book, Muscles and Molecules, Uncovering the Principles of Biological Motion, won an Excellence Award from the Society for Technical Communication. His 2001 book, Cells, Gels, and the Engines of Life, and his newest book, The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor, won that society's Distinguished Award, their highest distinction. The latter book went on to receive the World Summit Excellence Award. Pollack received an honorary doctorate in 2002 from Ural State University in Ekaterinburg, Russia, and was more recently named an honorary professor of the Russian Academy of Sciences and foreign member and academician of the Srpska Academy. He received the Biomedical Engineering Society's Distinguished Lecturer Award in 2002. In 2008, his colleagues chose him as the recipient of his university's highest annual distinction, the UW Faculty Lecturer Award. Pollack is a founding fellow of the American Institute of Medical and Biological Engineering and a fellow of both the American Heart Association and the Biomedical Engineering Society. He received an NIH Director's Transformative R01 Award. He was the 2012 recipient of the Prigogine Medal for Thermodynamics of Dissipative Systems, and in 2014 he received the Scientific Excellence Award from the World Academy of Neurotherapy, as well as a Dinsdale Prize from the Society for Scientific Exploration. He has presented 2 TED Talks on water. In 2015, he won the Brandel Laureate Award, previously bestowed on notables such as Nelson Mandela, Hillary Clinton, and Steve Jobs. In 2016, he was awarded the Emoto Inaugural Peace Prize, and more recently, the Lifetime Achievement Award from the Chapel Natural Philosophy Society. He appears briefly in the 2016 Travis Wright sports action film, The Fourth Phase, named after his recent book. And he is included in the 2019 listing OOOM magazine as one of the world's 100 most inspiring people. In 2020, he presented his work at the Majlis by invitation from the Crown Prince of Abu Dhabi at his royal palace, and more recently in 2023 at the United Nations. Let's get started. All right, welcome everybody to another episode of Healing Intentions. This is your host, Dr. Adrian Mehmedi, and today I have a really amazing guest. I'm super honored to have on to the podcast, Dr. Gerald Pollack. Welcome, Dr. Pollack.
My pleasure. Great to be with you, Adrian, and happy to try to answer your questions.
Absolutely. Yeah, I'm really glad to have made this happen. I have seen you speak a couple of times now at the Naturopathic Medicine Institute. They've put together the Vital Gathering conferences, which have been just absolutely amazing. Really awesome group of people, amazing information shared, and, really passionate about all of the topics that are covered, but one of my big passions particularly is the topic of water, and I know that's something you've dedicated your entire life to studying, and so it's really an honor and just so grateful to you on that.
Just one correction. It's been a couple of decades, but not my entire life. If you look at my gray hair, you'll see that I've been in business for more than a couple of decades. We studied my initial research area was muscle contraction and how at the molecular level, how the molecules would interact to produce force and motion. So that was the first half of my academic life, and water is the most engaging second half.
Yes, correct. Yeah, thank you for that correction. You're absolutely right. And you did give your presentation on the muscle contraction end of your work as well, which you cover in your book, Cells, Gels, and Engines of Life, which I haven't read yet, but is one of your earlier books. And so, yeah, a lot of other previous work. I guess I just went right to the water part because I'm the most excited about that.
Well, okay, no problem.
So your really famous book that I have right here, The Fourth Phase of Water, is kind of where we'll get started on this podcast and talking about your discovery with the fourth phase of water, which, as it says on the cover of the book, the most significant scientific discovery of this century, which, is a pretty big statement by Mei Wan Ho. And, just I love that. And so why don't you go into just as brief as you can of a summary of what the fourth phase of water is all about and anybody that hasn't heard about it, and we'll kind of go from there.
Well, as brief as I can.
Right,
That's the difficult part.
right.
That's the challenge. Um, let's see, I'm trying to think of the best place to start. And I guess the best place to start is at a meeting in Hungary. And a Hungarian guy who worked in my laboratory, just as I was picking him up from the airport and driving him and his wife to my home to stay for a couple of weeks until they could find their own lodging. He was to work in my lab for some period of time. And he said, on the way, he said, there's a meeting in Hungary and you should go. So my question, why should I go? And he said, well, the meeting is to commemorate the life of a scientist, a guy named Ernst, and his fields were kind of divided. He was a well-known scientist, highly respected, and his fields were muscle contraction and water. They have nobody to represent muscle contraction, and so why don't you go? And maybe you could represent it. And his idea about muscle contraction, Ernst's idea, was not too different from my ideas, which deviated radically from the mainstream view. And of course, we had evidence, and so I thought for a few microseconds, and I said, "Sure, why not?" So I went. I delivered my talk, and I think it went reasonably well. Not too many people, I think, were interested in the subject. The subject that interested most people was water. That was his second area. And there I met a guy who imprinted my scientific life in a really major way. His name was Gilbert Ling. And Gilbert came from China. He was in the first cohort of scientists, young scientists to be chosen from throughout all of China to study in the US. And there was a physicist, Yang, C.N. Yang, and the physicist won the Nobel Prize in physics. But in fact, he was better known for the fact that at age 80 something or other, maybe late 80s, he married his translator who was age 30.
Wow.
So that made a big splash throughout China, more than the fact that he won a Nobel Prize.
Mm-hmm.
And there was some rumors circulating throughout China that she was pregnant,
Mm-hmm.
or she became pregnant. I don't know what the truth of that. Oh, so he was the first guy. The second guy was a chemist. They chose a physicist, a chemist, and a biologist. And the chemist, I'm afraid I don't remember his name, but a Chinese student of mine told me that he also won a Nobel Prize. So, these were really special people. And the third one, the biologist, was Gilbert Ling.
Mm-hmm.
And based on his discoveries and inventions and what have you, he should have won at least two Nobel Prizes. But he was passed over because his work was too controversial. So I heard from him, and he was talking about water. And I knew beans about water. All I knew is that we were two-thirds water by volume, approximately. But I listened to him and I couldn't believe what I was hearing. He was saying that inside the cell, that the water inside the cell was not um, like ordinary um, uh, liquid water, like what I'm drinking here.
Mhm.
Um, that in ordinary liquid water, the molecules are randomly oriented and they're bouncing around a fierce number of times per second or even per femtosecond. He said, no, that's wrong. It's not like that. Inside the cell, the water molecules are lined up like soldiers at attention.
Mm.
And he explained that it was not unreasonable because if you think of the water molecule as a dipole, like a bean with plus at one end and minus at the other end, you could easily imagine how these would be lined up plus next to minus. And he said, not only are they lined up, but they're lined up for a tremendous distance, maybe 100 or 1,000 molecular layers. And if you ask me, I'll tell you about evidence that actually it's hundreds of thousands of molecular uh, layers, not just 100 or 1,000.
Wow.
So anyway, that's how we got started, and I was just so impressed by this. But on the other hand, I'm easily impressed, and so what I did was I gave one of his books. He had written 3 or 4 by that time. I gave one of his books to some of my students in the lab to get feedback to see if my enthusiasm was really justified.
Mhm.
And their responses were uniform. If this is right, then all of biology is wrong. And it looks like he's right because there's a lot of evidence for it. And I heard some of that evidence from various other people at the conference who presented supporting evidence for Ling. So I was really turned on, and
Mhm.
I thinking, I can't let this go because this is so important. And if he's right, then we have to begin all over again with biology.
Mhm.
The water. If you read the textbooks, water is considered merely as it doesn't do anything. It's just the background carrier for all the important molecules of life, quote unquote,
Right.
like proteins and nucleic acids and such.
Mhm.
And so there's a vast difference between that view and the view that was being espoused by Gilbert Ling and other colleagues who were not in Ling's domain, but independent scientists who had evidence to support his point of view.
Mhm.
Um, so getting all of this feedback from the students, I thought we have to do something because I simply can't let this go. We'd spent at least 2 decades studying muscle contraction, and the most prominent molecule in muscle are not myosin and actin, but water. There are many more water molecules than any molecules, and
Right.
and if you think about it, the figure that's usually given for the amount of water in our bodies is like 2/3, but 2/3 is by volume. Now,
Right.
if you were to take these tiny water molecules um, and line up all the molecules inside the cell, one by one, more than 99% of those molecules are water molecules because the water molecule is so small that you need a lot of them to make up that 2/3 volume.
Yep.
So,
Yep.
the textbook says that, water, 99% of our molecules, which is true not only in muscle tissue, but pretty much all tissue, 99 out of 100 molecules don't do anything. That seems moderately preposterous that that's the case. So anyway, the first thing that we did, because we had no money to do experiments, and I really wanted to follow up,
Mhm.
and we did soon after. And by the way, just to um, give you advance warning, we found largely that Gilbert Ling's ideas were justified. However, there were some fundamental differences that we discovered, which I'll tell you about. make a giant difference in how we think about water.
Okay.
So I'll tell you later if you ask me. Or at any rate, first thing I did was to write a book to explain Gilbert Ling's ideas, and that was called Cells, Gels, and the Engines of Life.
Mm-hmm.
And first half of the book was designed to do that. The second half was actually to say, okay, given Gilbert Ling's ideas, how do we understand what happens to when cells get activated to do whatever they're designed to do? Like, for a muscle, muscles contract, and for a nerve conducts, and
Mm-hmm.
for a secretory cell, the cell secretes.
Right.
And then, so the second half of the book was designed to show that what really happens is that this structured kind of water, he called it structured water, sort of crystalline and like, undergoes so-called phase transition. Everything in the cell transitions. The water becomes ordinary liquid water transiently, and the proteins undergo a conformational change, which produces the action of the cell, and then it retreats back to the original. So that was the book. Gilbert Ling hated it. Um, he, I think he hated it because it was stealing his thunder. The book was quite successful,
Mm-hmm.
not as much as the book that you showed, which is extraordinarily successful. But it it um, it tried to explain Gilbert Ling's ideas, and Gilbert was upset with the whole thing because it seemed to steal his thunder. His books were really complicated to read, and that was the motivation behind writing my book. I wanted to make his ideas understandable, and of course, I had to simplify somewhat. And Gilbert was unhappy that I failed to mention his name in every paragraph. That's how it goes. So people have egos, and
Oh yeah.
and I think the book did a lot to advance his points of view, even though later we found some aspects a lot different from what he was talking about.
Right.
But eventually we made friends. It was when we had clear evidence for long range ordering of water that he jumped out of his seat, and it was practically um, uh, we couldn't hold him back. His enthusiasm was so great. He was jumping up and down, saying, "Well, finally, my ideas have been confirmed by someone else in another laboratory." And so he was really enthusiastic. Unfortunately, he passed about 5 years ago, and he really left a mark. So that's how we got into it. A few years later, we managed to get some funding, and we started studying this water in earnest. And to sort of complete the story, the skeletal outlines of the story, we started with Gilbert Ling's idea. And Gilbert Ling said inside the cell, he said, the water molecules are ordered like soldiers at attention. And ordering is sort of like a crystal or a liquid crystal. And crystals have a tendency to exclude contaminants. So, for example, in ice is a crystal. And if the crystal forms from water that contains contaminants, the contaminants are excluded from the water. They're pushed out because otherwise it wouldn't be a pure crystal if it had contaminants in it. And other crystals do much the same. So we were looking for an experimental setup in which we could possibly find this kind of exclusion. And by dint of good fortune, I found the right postdoc who had the right experience and such. We found it quickly. What we did was we just took a chamber full of water, and as for contaminants at first, we used little spheres called microspheres, and these spheres are used throughout science. There's nothing really exotic about them. And so you have a suspension of these contaminant particles in water, and we immersed a gel. It was a polyvinyl alcohol gel, but it doesn't really matter because we found eventually the same with so many different kinds of gels. So we put the gel in, and we found very quickly that next to each surface of the gel, the microspheres became excluded. They were pushed out and pushed out to, at first, we found a distance of 200 or 300 micrometers. And 200 or 300 micrometers, you could see it with your naked eye. It's really large. Later, we found exclusion, these zones of exclusion up to maybe a millimeter or so. And in some special circumstances, even as much as a meter. So just growing out to that distance. So we found it. Of course, we didn't know at first. We couldn't be sure that this was the same as Gilbert Ling's idea of what was causing this, namely the structuring of water. But anyway, that's what we found. We kept finding it, and someone suggested, a colleague from Australia, he said, well, why don't you give it a name instead of going through this elaborate description of what you did? Call it something. And obviously, because it excluded, we called it the exclusion zone, EZ, easy to remember, but that doesn't work so well in Europe, where it's EZ. Anyway, we called it EZ water. And later, when we confirmed that the properties of this water were just absolutely grossly different from liquid water, and we then called it fourth phase water because it had it was basically water derived from water, and it and all of the properties we by now at least a dozen different properties were distinctly different from liquid water. So that's how we got to the fourth phase of water. And if I may have license to just go on a little bit.
Please do.
Yeah.
Of course.
So I mentioned that a few features were different from what Gilbert Ling, he called it structured water. That's a kind of generic term. And it's the same as what we now call fourth phase of water, or EZ, exclusion zone water, all pretty much the same. But we found some interesting features of it. First of all, I have had a lot of experience using microelectrodes, the kind glass microelectrodes that taper to a point, sticking it in cells and measuring electrical potentials. Parenthesis, invented by the same Gilbert Ling, and used broadly, and that alone deserves a Nobel Prize because it really changed biology. Anyway, having had experience with that, I thought, let's stick it into the exclusion zone and see what we find. And we were shocked, so to speak, because electrically shocked, because it was not neutral. It starts with water, which is neutral, and we fully expected that zone would be neutral, as Gilbert Ling implied or surmised, but didn't measure. But we measured it, and it was negatively charged. And so I was scratching my head, how is this possible? And the only way it's possible, if the EZ is negatively charged, that some other region must be positively charged, because you started with water, which is neutral,
right.
And you can't suddenly start with something that's neutral and then wind up with something that's negatively charged, right?
Right.
You need, and we found that right next or just beyond this exclusion zone were positive charges. So we got negative and we got positive. And that's a battery. And so I say it softly, but with actually a loud voice, because the water, if it's a battery, it contains energy, and that energy could be delivered, and we actually demonstrated indeed that it was indeed delivered in certain ways biologically, offering an opportunity for a different kind of energy from the energy we think about to power biology. Big deal. But if you think about it, it's not so radical, because the same thing happens in photosynthesis. Light comes in step one, among the, I think, 20 steps of photosynthesis. Step one is light coming in and splitting water into positive and negative. And I was awakened to a problem that has rarely, if any time, been addressed by the biological community. When you separate negative and positive charge, all they want to do is recombine, right? We were taught in middle school that plus and minus attract one another. So you try to separate them, as pretty much everybody agrees is the first step of photosynthesis, but never addressed is how they remain separated, because you'd expect that they would recombine instantly. And we found later that the reason that they don't recombine in our phenomenon, which seems to be pretty much similar to the first step of photosynthesis, the reason is that the fourth phase, or easy water, is a very dense structure. We know the structure, at least we think we know the structure. It's a sheet-like structure where the sheets stack on one another, and each sheet is a honeycomb with hexagons. And those honeycomb, the openings of those hexagons are so small that the positive charges can't enter. So it's a physical effect that occurs that doesn't allow the positive charges to recombine with the negative ones. And I think it's possible or likely that in the first step of photosynthesis, the same thing happens. And I think it's possible that the first step of photosynthesis is just one example of a more general finding that I've been discussing with you, that it's not just in plants, it's everywhere. It's inside animal cells, plant cells, and even outside of biology, which we've demonstrated. So it's a big deal because it's an energy source. And a lot of people don't know this, but the general idea of where the energy comes from is from ATP. And I think that was almost like 80 years ago was discovered. And the idea is that there's a high energy phosphate bond in ATP, and that bond releases energy, and that's where we get our energy for everything.
Right.
What people don't realize is that there was a challenge to this, and the challenge came in the 1950s or 60s by two guys who actually were in the muscle contraction field, or are. I've kind of lost contact, prominent people. And they investigated this exactly in muscle contraction, where energy is obviously really important. And they found that there was no high energy phosphate bond, that all the bonds and ATP were similar to other organophosphate bonds, and nothing special. And I don't know why, but I guess it's because there was huge interest in ATP and a lot of devotion to that idea, that this evidence, which was clear and extensive, was just ignored. And since I know the two investigators, I know that these two people are kind of slightly diffident about reaching out and saying, look what we found, but still in the literature and still clear, and anybody could look it up. And the names are Morales and Podolsky. So it's possible, if they're right. I don't know if they're right or if they're wrong. Needs follow-up desperately, because everybody wants to know where our energy comes from. And it may indeed come from ATP as originally discovered, or that may be a red herring. It may be completely erroneous. And if it is erroneous, and again, we're not sure, this needs follow-up. If it is erroneous, then the possibility exists that the energy is electrical, as we've been talking about, plus and minus, a battery that we actually get our energy, or most of our energy, or possibly even all of our energy, from electrical sources. So maybe I'll stop there, and because I think you've got a few questions to ask
Yeah.
me. But
Yeah. That's
can I
great.
just one more point?
Of course, please.
That all batteries need charging, right? You can't get a battery from nothing. You need energy. You can't create energy. All you can do is convert energy from one form to another form. You
Right.
know, you put in, well, okay, and that's one of the areas of physics where I have no problem with, because it makes a lot of sense. You can convert one energy to another. So we light the light bulb by supplying electrical energy, and thereby we get light and heat,
Mm-hmm.
for example. So where does the energy come from to build this battery, this water battery, if you will? And we found that it was actually an undergraduate student who was working in the laboratory, and I guess he was bored. He was he was working with a chamber, like I described a few moments ago,
Mm-hmm.
where he puts a gel or a polymeric surface or a biological surface, and he's looking at the exclusion zone. And I don't know if he was bored or maybe just curious, but he noticed a lamp sitting next to him, a gooseneck lamp. He took the lamp and he shined it on the chamber, and he noticed that the region that was illuminated, the exclusion zone, grew enormously. So he ran into my office, called me, and I looked, and I was astonished because we had been looking for the source of energy, and it looked like he found it. Light. Light came in, just like photosynthesis first step. Light came in, um, and the light grew the exclusion zone. And at first, we had to find out whether it was correct or not. And we did some more sophisticated experiments, I should say more detailed experiments. And we were looking, the lamp has a series of wavelengths. And the natural question was, which wavelength is the most important?
Mm-hmm.
And we studied it extensively, and we found that we started from the short wavelength and from ultraviolet through the visible spectrum, and at the long wavelength, um, infrared energy.
Mm-hmm.
Ultraviolet didn't do hardly anything, and visible light mostly very little, except toward the reds. There began to be an expansion. And once we got to the infrared region, it was even a simple LED lamp producing a very small amount of infrared energy could expand the exclusion zone enormously. And we could expand it by a factor of 10 with a very, very simple infrared lamp.
Wow.
So it didn't take a rocket scientist to figure out that it looks like the energy to charge this water battery, the energy came from infrared, or at least principally from infrared light. So,
Mm-hmm.
that's that. You might say that's the essence of the story. And if you have a hydrophilic surface, like as for a gel or a biological surface next to water, the water, in the presence of infrared energy as the source of energy, the water splits into negative and positive, negative EZ and positive charges, uh, constituting a battery. And so it's infrared energy that charges the battery, and that battery is ready to deliver energy to the cell or what have you. So I think I'll take a breath for a moment and let you answer any questions that you might have on your mind.
Yeah, wow, thank you. That was great. Yeah, you covered a lot there, so a lot of different paths we can go, but I mean, that makes a lot of sense. So just on a practical level, how does somebody know if they're consuming easy water or not? Like, is it something easily like you can tell the difference between easy water or not, or something that needs to be tested? How, like on a practical level, is that something people can know? Like, I'm getting more easy structured water into my body, or is it not such a simple answer?
Well, it could be a simple answer, but it's not there yet. And the simple answer is something called the UV vis spectrometer.
Hmm.
This is a device that inputs a series of wavelengths of light into a chamber
Hmm.
uh, and measures what's absorbed and what comes through.
Okay.
And it turns out that easy water absorbs light in the UV range at 270 nanometers. We have many examples of this. So if you want to test to see whether a sample of water contains some easy water in it, you put it through this device, and the higher the absorption peak at 270 nanometers, the larger the fraction of easy water. We haven't found yet a convenient way of obtaining pure easy water. We're working on it, or at least what I mean is a way that's genuinely practical. But
Right.
if you have access to a UV vis spectrometer, then it's very easy to tell whether a sample does or doesn't have easy water. It's not quantitative, it's only semi-quantitative. But if you see a sharp absorption peak at 270 nanometers, you can be assured that you've got a pretty substantial amount of easy water in your water sample. So that's the way to do it. And I just been thinking the past week or two that um, this can actually be implemented very simply by an entrepreneur who wants to tackle this, because we're only interested in the region around 260 to 280 nanometers. And it may be possible to build a simple spectrometer, simple and cheap, that does this automatically. And if you sell enough of those, you could actually do pretty well if that's your interest. And that actually would be very useful, because so many people want to know about easy water and which samples of water contain easy, which ones don't. I get questions on that topic practically on a daily basis. Which which source of water should I drink that contains easy water? And
Yeah.
my response is, I don't know. I can hypothesize, but the only way you can know is to make the measurement. I've
Yeah.
seen some measurements, particularly of spring waters. A lot of people tout spring waters as being good for health. Well, it seems that the spring waters differ from one another. You can have some spring waters that contain no obvious easy,
Mhm.
according to the spectrometer, and others that contain an extremely sharp peak, tall, sharp peak of absorption, which contain a lot. So spring waters are not uniformly full of easy or fourth phase water, but
Mhm.
some of them. So a device like that would be spectacular.
Okay, that makes sense on to be able to test the easy water if it's there or not, and then to go following up with what you just brought up, the different ways you can get water. I know that's a whole big topic and we could go on with that for a long time, but just briefly, I know you get asked all the time, but what are the best sources of easy water? Spring water, we don't know. Some are, some aren't. Are there other ways that you found? I know there's a lot of devices out there that claim to make, there's a lot out there. What I'm discovering is the power of hydrogen in water. It seems that hydrogen in water is a very powerful therapy. There's a lot of research that's been done on molecular hydrogen and biological health. And there's different ways to get to hydrogen water. It seems like there's the Brown's gas that gets put into the water, which creates hydrogen. There's the electrolysis of water, so you can split the molecule and then hydrogen gets created that way through adding in electricity into the water. And then there's the deuterium depleted water, which I don't quite understand, but is something to do with hydrogen as well. And so, in my understanding, is all of those have something to do with hydrogen. And my understanding is that all of those would have some aspect of easy water or another. So, what do you have to say about all that? I know there's a lot there.
Well, I don't know where to start. I guess uh, um, deuterium depleted water we're studying right now. And
Mm-hmm.
the preliminary evidence looks preliminary. I don't want to say for sure because we don't know for sure.
Mm-hmm.
But in the experiments we've done so far, it looks like deuterium depleted water builds EZ. You get a bigger EZ when you start with deuterium depleted water compared to ordinary water. Again, with reservations because the final evidence is not in, but it's looking that way.
Mm-hmm.
I actually shouldn't be talking about it because until we're firm on the evidence.
Sure.
Okay, and for me that makes sense because we were talking a moment ago about contaminants,
Mm-hmm.
and if you have if the EZ builds with contaminants, you could imagine that it won't build as far because these contaminants are kind of interruptions of the crystal,
Mm-hmm.
breaks in the crystal, and that limits the growth. But if you don't have deuterium in the water, then you have a purer crystal, and it should be able to grow some more. So that's what I have to say, with the caveat that we're not sure yet about this. Now, hydrogen water, I heard about it 10 years ago, maybe, and I must admit I've not studied it. However, I'm not sure it's really hydrogen water. So in order to create this, um, what you do is put a potential difference across the water, and we assume that the potential difference creates the hydrogen in the water. Well, we found something entirely different from what we expected. We took some water and we put one electrode, had two electrodes separated by a certain amount.
Mm-hmm.
And we applied potential difference between those electrodes. And what we found, maybe to our surprise, but not, is that instead of getting gas coming from the middle, we found that next to the negative electrode, negatively charged EZ built, and next to the positive electrode, I didn't mention this, but there is a positive EZ that you can have. It's unusual, but there are certain circumstances where it happens. And these two began building from each electrode and continued when they reached a merger point, they didn't recombine. You could see that one of these zones actually invested itself into the other zone. And they, just like I was talking about before, there's no recombination. So
Mm-hmm.
if this is how the hydrogen water is supposedly created, we don't see any hydrogen. All we see is EZs building up and coming together and not recombining. So I'm not really sure about hydrogen water. I think, the idea is that it comes from hydrogen, but in our experiments, they seem to question that.
Mm-hmm.
Uh, there was a third aspect of
The Brown's
of
gas and
Brown's
putting
gas. So
into the
one of
water.
my students or postdocs studied Brown's gas for um, the better part of a half year, and um, couldn't didn't find excuse me uh, didn't find anything that looks like hydrogen. It's not clear what Brown's gas really is. I don't think anybody knows at this point, but
Okay.
he was unable to actually determine what what is Brown's gas. So
Mm-hmm.
So, I know that a lot of people are excited about the idea of hydrogen, but I think it needs to be studied some more because I'm not sure that what people are considering to be hydrogen gas is actually easy water.
Right, right. And I just I understand what you're saying. It makes a lot of sense. And I just want to make one other point that I asked you there in person at the conference, and because I've had the Kangen water, Enagic water ionizers in my life for the last 13 years, and I'm a huge fan. I've seen them do a lot for people's health. And to my understanding, everything you describe about easy water is exactly what this machine is producing. You know, it's negatively electrically charged water that's structured, that is hydrating our body at a much better cellular level. And it's something that, like, when you drink the water, you can literally feel it. And when you test it, you know, you can test that it's negatively electrically charged. And you can test that there's hydrogen in the water with the ppm meter, you know. So to me, I understand that it is this like developing this water, but like you said, in person, maybe you just haven't found ways to test for it and find the ways that it is the easy water. But I don't know. I think there's something interesting there. I'm not, you know, religious about it and like this is the only water and the best water and only everybody needs to drink it. But I do believe that there's something to it that maybe we just haven't discovered exactly what is going on. But with your discoveries in easy water and what this water I understand is doing, I think there's a lot intersecting there. But I don't know.
Yeah, well, I know the Enagic a machine, and it's exquisitely designed and wonderful. And I must admit, I had been drinking alkaline water myself for a number of years, and until some home renovation made it impossible to hook up easily, I stopped. And I had the same idea or a similar idea to you about testing to see at least whether that water with high pH and therefore negative charge, whether it contained easy water. We did one quick test, and early on, the test didn't show that, but we need to test it more extensively. We haven't gotten to it yet because I suspect that you're right. I suspect, or at least partially right. I suspect that the alkaline water, negatively charged water, is actually full of easy water, and that the health benefits, which seem to be extraordinary, there's some controversiality about it, but
Sure.
I know the guy who studied it in Japan. Unfortunately, he had some medical issues and is unable to communicate now, but he spent better part of his life, and he was telling me that in Japan, if you go to a physician and you've got any kind of problem with your gastrointestinal system, from your mouth to your butt, anywhere, the government will actually pay for you to drink this water. And
Wow.
governments don't usually do that unless there's clear evidence. And he said the evidence was so extensive and so clear. So
Yeah.
I mean, it looks as though there's something going on there. There have been some suggestions that over the long term, maybe this is not so good for you, but I haven't researched them to see if there's anything to them. Anyway, I was drinking that myself for quite a few years.
Awesome.
I guess I did remain healthy during that time, so maybe the Enagic water is what did it. I'm not sure.
Yeah,
So
I love it. Thank you so much for answering that. That's great. Staying on the topic of controversial topics, which I told you at the beginning before we recorded, I love to get into, but you said no worries at all, which I love. Why do you think that research on the idea of water holding memory has long been criticized?
because because uh, the only water in biology that had been known until we discovered the easy water, or known and accepted, it was water in which the molecules were randomly oriented and moving around, bouncing around at a fierce number of times per second, or per millisecond, or microsecond, or even femtosecond. And when you have a situation like that, it's impossible to conceive that the liquid water can have memory. It doesn't make sense, because you're constantly mixing, and if you're constantly mixing that way, it seems unreasonable. So when Jacques Benveniste produced clear evidence that water contains memory. And he told me, he said, I shouldn't have used the term water memory because it's too provocative. um, and then, uh, well, so he was shot down by the editor of Nature in a long and interesting saga that actually ruined his reputation. So Jacques Benveniste was an esteemed French scientist who had a laboratory of 50 people, approximately, and um, uh, and because he professed that his experiments showed that water had memory, and other laboratories actually contributed to this, did the experiments independently, got the same results. Still, the editor of Nature would not believe it and would not accept it. And the reason I think one might argue that there was some bias of the editor against anything that seemed new. I'm not sure if that's true or not true, new and revolutionary, but also the idea of liquid water containing memory didn't make any sense. So Benveniste lost his career and died prematurely, was despondent because of what happened. It just ruined a brilliant career. And there are many reports now about water memory. And the first is a joint paper by a group of people, including doubters throughout Europe. They published a paper together confirming the original Benveniste result. So at our conference, at our water conference, which, by the way, is annual, I'm the scientific organizer, and it'll be in Lisbon, lovely city, October 16th through 19th, if anybody's interested. The website URL is www.waterconf, C-O-N-F, one word, waterconf for conference, .org, not .org. So anybody who's interested, you're more than welcome, and it's an exciting conference. And the reason I mention it is that each year, practically, we have 2 or 3 people presenting their own evidence for memory of water.
Wow.
So at that conference, it's considered to be a fact. Pretty much everybody presenting at that conference, and most of the people attending the conference, it's a very friendly place.
Nice.
Take this as a fact, and the fact, and the water memory, the most prominent guy. There are a diversity of people studying water memory, and perhaps the most famous of all is Luc Montagnier, who came to our conference over a decade every year and presented his stuff. And he won the Nobel Prize for a Nobel Prize for identifying HIV. That was some time back, but he in his later years, he passed a year or two ago. In his later years, he studied water and water memory, and his result was astounding. What he found, he took 2 sealed tubes. One of them contained DNA and an aqueous buffer, and the DNA was a short strand, maybe 100 base pairs or something like that. And sitting near it was a container of water. Both were absolutely sealed, so nothing could, no chemical communication between the two. So he applied a generic kind of energy, like 50 hertz or 60 hertz for a day. And then he took this water and he used it in the PCR, combining it with the PCR chemicals. PCR, everybody knows about it because of COVID.
Right.
And he combined it to amplify the DNA, and the new DNA had the same sequence as the DNA that was sitting next to the water. No chemical communication, only some kind of either electromagnetic or whatever. Now, that result is astonishing, and I think many people think it can't be true because there's just too much information that would need to be passed. On the other hand, there are at least 3 publications now, 2 from Italian groups and 1 from Chinese group, that confirmed the result. So, if we take confirmation by other laboratories as some indication that the finding is correct, then it appears that that's correct. And this is a Nobel laureate to whom we have to confer or some kind of respect to the guy doing a pioneering experiment confirmed by others. Water memory appears to be true, and even if you consider the spiritual work of Masaru Emoto, who in a couple of weeks we're celebrating the 10th anniversary of his passing in Salzburg. I will be there for the symposium speaking.
Awesome.
He claimed to be a spiritualist, not a scientist. So many people didn't take his work seriously, but what he did, for those who are not so familiar, because his work is pretty well known. So
Oh, yeah.
he would put his intention to a beaker of water or a petri dish full of water, and if the intention was positive, like he was thinking about peace or I love you or something, and he froze the water, the crystals were beautiful. And if he said, I hate you, or something negative, the crystals were ugly.
Mhm.
And he was a spiritualist, and therefore many sciences didn't take him seriously, but that's essentially was his contribution. So anyway, there's a lot of evidence for water memory. And now there's newer results by someone from New Zealand, Veda Austin, and she's written a book, and I just got a copy in the mail yesterday, showing beautiful images and along lines that are not so different from what Emoto showed, but she well, I leave it to those who are interested to check out her book and her results, because they're really astonishing. And she's going to be presenting at our water conference, and she's going to present scientific evidence for what she's doing. In other words, repeatability. Scientists always look or ask the question, how repeatable is this? And if you put a banana beneath some water and you freeze it, and the ice shows the image of a banana, your obvious question is, well, is this 1 out of 500,000, or can you repeat it? And at our conference, she'll be presenting the degree of repeatability, which appears to be very high. So water memory, a lot of evidence for it. I think the reason, sorry for the long answer to your short question, but I think the reason people could not imagine that it could be true is they thought of water as being only liquid water, but easy water is different. It has structure to it. And in fact, I've been arguing at various conferences that the structure is pretty much resembles a computer memory structure. There are many similarities between the two. And if the evidence really shows that water contains memory, I think it's the EZ water is the water that is the substrate that holds that information. So maybe I should end there.
Wow. Yeah. And that makes a lot of sense. If that were to be true, that memory holds water holds memory, then that would be a great explanation for how homeopathy works. And one of our favorite tools as naturopathic doctors, and it's a medicine that's used all around the world by hundreds of millions of people. So obviously there's something to it. The whole placebo effect and all of this talk that scientists try to just dismiss homeopathy as oh, it can't be. That's Luc Montagnier did some work, and we learned about him in our homeopathy classes, and that the experiments he did kind of helps to explain how homeopathy could be working. And so it's really exciting, in revolutionary times. had homeopathy professors at school tell me they will discover how exactly homeopathy works here in our lifetime, and whoever discovers it will win the Nobel Prize. So it's pretty exciting.
Well, I think Nobel Prizes are not often given to radical revolutionary findings, but maybe
Right.
I'm wrong about that. I'm not sure, but the argument about placebo effect seems specious because animals, veterinarians use homeopathy, and I know several people
Yep.
who are in business in the veterinarian homeopathy, and they stay in business. So, if your horse has a problem and the homeopath solves the problem, you're going to bring the horse back.
Right.
And placebo effects in a horse or a dog seem unlikely.
Yeah,
So that's
exactly.
a short response to that. And I'm in agreement with you. You need some sort of memory, and I think that memory resides in easy water.
So, do you think that cellular dehydration is the root cause of sickness in people?
Absolutely.
Yeah.
Absolutely. Yeah. So, we talk casually, um, about getting dehydrated, and you really need to remain hydrated. And I suffer that problem myself. That's why I've been trying to drink more water.
Cheers.
Yeah, you got it.
Mhm.
Um, and here's the reason. So I mentioned to you that in my book, The Cells, Gels, and the Engines of Life, I talk about how cells undergo a phase transition, that their action is mediated by a transition between in the I hate to use the word relaxed state because that applies only to muscles, but unactivated state, undergo a phase transition to the activated state when the EZ water is transitions into ordinary liquid water and then back again. But that transition can't occur if you don't have enough EZ water. See, so so therefore, if you don't have enough EZ water in the cell is not functioning properly.
Mhm.
And that's how the idea of EZ water manifests as if you don't have enough, you've got dysfunction. So, we all know that if we're dehydrated after maybe 2 matches of tennis or something, we can't do anything. We sit down at the bench, we drink a couple of liters of water, and we're kind of back again. The water um, rehydrates, it builds EZ water in your cell, and your cell is back from dysfunction to function. So that's is really important. And if I may extend the argument, we've been thinking about cancer in particular, and um, so let me just expound on that for a bit. Cancer has been studied mostly as a genetic disease,
Right.
and 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 50 years ago, or more than 50 years ago, President Nixon, if you pardon the expression, um, declared war on cancer, and the
Yeah.
war has not been won. I don't think anybody would argue there have been some advances, but the war has not been won.
No.
So what's going on in cancer? Well, one of the characteristic features of cancer is that the cells keep dividing. You get a tumor.
Mhm.
So why do the cells keep dividing? And I'm going to relate this to the water in the cell. Why do it keep dividing? Well, so a guy named Clarence Cohn 50 years ago did experiments on exactly this question. He took various cells and he could change the electrical potential of the cell. He could impose some features that either increased or decreased the electrical potential. And he found that if you increase the magnitude of the electrical potential to, let's say, 100, minus 100 millivolts or minus 150 millivolts, the cell would never divide. If you
Mm.
reduce the electrical potential to something like 10 or 15 millivolts negative, the cell would keep dividing. So it looks like, I mean, from his experiments, you'd think that if the electrical potential of the cell is small, then the cell would keep dividing. The magnitude I'm talking about, forget the sign for a moment. Now, so the question is, what causes the electrical potential of the cell? And we all learned that the electrical potential of the cell has to do with pumps and channels in the cell membrane. I've argued in various venues and publications that that's erroneous for half dozen different reasons. One reason is if you take a gel, which is just like the cytoplasm, it's gel-like. If you take a gel and stick an electrode in, you measure minus 100 millivolts typically, just like the cell. There's no membrane, no pumps, no channels, but you get the same electrical potential. So it's kind of hard to argue that the electrical potential in the cell comes from the membrane. There are a half dozen other arguments, but I don't want to take the time to go through them. They've been published in various places.
Sure.
So where does electrical potential come from? Well, the cell is full of easy water. Easy water, it typically, especially biologically, negatively charged. So, it's not a far reach to say, well, the reason that cells have a potential of, let's say, 50 to 100 millivolts negative is because it's filled with easy water that has negative charge. So, you take a container and you fill it with something negative and you stick an electrode in it, you measure negative. It's not complicated.
Right.
It's very, very simple.
Mhm.
Now, so typical cells have a electrical potential minus 50 to minus 100 millivolts. I looked at a review article which reviewed all the evidence from many years on cells that divide and cells that don't divide.
Mm.
And without exception, the ones that divide, either because they're a tumor or because they're proliferating kind of cell like embryonic cells, they all have very low electrical potential, 10, 15, 20 millivolts negative.
Mm.
And the cells that don't divide, like muscles, or don't divide often,
Right.
muscle cells and such, minus 80, minus 90, minus 100 millivolts. So if you think about it, and you put two and two together, the reason that tumor cells, that cancer cells divide, is because of their low electrical potential. And the low electrical potential means they don't have much easy water. So they're pathological.
Mhm.
So if we're right in this thesis, it means that an expedient, an anti-cancer expedient, is build easy water in your cells. And there are half dozen simple ways of doing it. There are other ways of doing it. In the manuscript that I've written on this subject, I list about maybe 10 different ways of doing it. The simplest is drink more water.
Mhm.
And there are others like, for example, expose yourself to infrared energy. Infrared energy builds easy water. And
Mhm.
I know some practitioners who do that. I met a guy in Germany, and he said young women who have cancer somewhere on their face, they don't want to have surgery. They come to him, and he treats them with infrared energy, and the cancer disappears. So,
Wow.
why should that be? And I think the reason is that is that infrared energy builds easy water. So anyway, I'm just giving you that as an example. The other pathologies pretty much the same.
Mhm.
Your cells are dehydrated, means they're lacking easy water, and you build easy water and you can reverse the pathology. That's the thing. Needs to be tested. We're hoping to test it. Getting money to hire the people to do these tests, I tell you, is a real challenge. It's almost impossible to get money from the granting agencies because it's the quote experts in the field who review and make judgment. And you know, they have toes that are fragile. I don't want people to step on their toes. And so you can imagine that the the reviews that come back were not enthusiastic. So it's only a matter of people of means who want to do something meaningful, and
Mhm.
so funding depends on that, and it's really hard to get.
Yeah.
So
Yeah, it's science, like you mentioned in your book, that science that just wants to stick with the status quo versus like trying to actually go beyond and move into the future. I love this quote you have here at the beginning of the book. Albert St. Georgi, Nobel laureate, discovery consists of seeing what everybody has seen and thinking what nobody has thought.
okay, well, I've got a couple more. This book
Yeah.
just arrived yesterday,
Oh,
in the mail. This is the next book, and this
awesome.
is a pre-publication copy, and uh, uh, it's not quite done, but almost done. And I just wanted to read to you if I can. I think I know where it is. I just want to make sure. A couple of other quotes that are in a similar vein.
Yeah. I
Uh,
love the title of
okay,
the book,
Mark
Charge.
Twain. I'm sorry.
I love the title of the book, Charge. That's awesome.
Well, thank you. Yeah, the real version should be published in about 3 months.
Awesome.
And okay, Mark Twain. It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so.
Mm,
And
right.
then the great physicist Richard Feynman, science is the belief in the ignorance of experts.
Mm,
So
hmm.
I kind of like those quotes, and they're in the same category.
I love
Anyway, I'm excited about this
I'm
next
really
book.
excited for that. Thank you for sharing. That's really awesome. I can't wait to read that. And going along the lines of Charged, another question I have for you is on electrolytes. And I think of electrolytes, putting minerals, electrolytes into our body as a way of helping to charge up our battery that our body is. So what are your thoughts on the best electrolytes out there? I know that's a big topic now, but when you're talking about electrolytes,
I can't really contribute anything in that vein because I've not seriously thought about it. Sorry.
okay, fair, fair enough. I thought maybe, just throw it out there. So the health implications for the fourth phase of water, the easy water, are obviously vast on a variety of different conditions. But anything more you want to talk about in that, like just potential health application implications, just on a high level? If what you're talking about is true, what does that mean for human health?
Well, it means everything for human health. It means that we've been on the wrong track. Um, Health is one of those issues that seems not to be improving, but the opposite.
Right.
Um, and you know, I guess that the bottom line is that people need to be awakened to the fact that something's wrong here. We're getting sicker and sicker, and we're not. We have all this medical technology and expertise, but it doesn't seem to be making a difference for us. It seems that it's going in the wrong direction. So something is fundamentally amiss.
Mhm.
I I I I think I'm not certain, but I think what we found is could be a key to moving in a different direction. And and the key, I think, also to if we're right, um, then the key is for example, organizations like National Institutes of Health need to change their point of view. There's nothing that I know of, zero, zilch, that's funded right now by NIH that deals with easy water or anything like that.
Wow.
I I I I feel confident that the word water is not in the vocabulary of some of the people who are um, setting the course of research, and
Yep.
I so much of it has to do with genomics, and genomics has gotten us somewhere, but not as far as we'd like.
Right.
And I think it's up to those granting agencies to recognize that there's something different that's going on there that has some capacity. Maybe it's not true, but maybe it is true, some capacity of going in a different direction and actually finding progress. They haven't done it. An example is I get asked almost on a daily basis, which water should I drink?
Mm-hmm.
And my response uniformly is, I don't know. I can um, I can suggest that if you drink water that's rich in EZ, that it will be good for health. But the only way, that's just my, you might say, speculation based on the evidence that we've obtained. The
Right.
only way to see if it's really true is to do a clinical test. So you take, for example, people with, let's say, colon cancer, uh, and you give 50% of them, you give um, um, one kind of water, water A, and 50% give water B.
Right.
And you could decide which waters you want to test. And after 1 year, you look at the results. Everything the same except the water that they drink.
Right.
It's not a complicated test. NIH is doing this all the time for various pharmaceuticals. They spend between the drug companies and the NIH, they spend an enormous amount of money on it. And testing waters in a similar way would be much cheaper. Should be done by someone who has no financial stake in any of the waters that are being sold.
Right.
And it wouldn't be very complicated, except for the fact that the word water seems to be out of the NIH vocabulary.
Yeah.
It's so important to do it, and I'm not sure, I'm not a marketing guy, but we need somebody to convince higher levels at NIH and similar organizations throughout the world that they need to spend at least a small fraction of their investment in water. So
Yeah.
that's what I would say to that.
Yeah, I would definitely agree. I think it's one of my favorite quotes is simplicity is the ultimate sophistication. I know it's a Leonardo da Vinci quote. And it's like, what's more simple than water? We think, right? Water is just water. But as we've just talked about over the last hour and 15 minutes, it certainly is not so simple. So people at the higher ups at the NIH and above, once they realize that, but we don't want to get into the topics of the money and the influence and the politics, but with all of that stuff, just follow the money. And it's like, who's funding the water research? It just isn't
Yeah,
happening, and so that's part of the problem.
it's part of the problem. Yeah.
So what do you think is next for just the water industry in general? Like, what are you excited about coming for the future here?
About the water industry.
Just
Um,
water in general, water, ways to detect easy water, ways to make easy water. Just what excites you about water in general going into the future?
well, what excites me the most, I guess, is the potential curative value, um, which needs to be explored further. But from the kind of practical point of view, if that's not practical, it's
Mhm.
very practical. But we know that um, water water is an energy source, as I've been discussing. And we have proof of principle. We actually tested to see, we stick one electrode in the negative zone, one electrode in the positive zone, and we get enough current out of that to light an LED lamp. So we know the proof of principle that we can extract energy, we can extract electrical energy from water. So what we're dealing with essentially is water and light. So um, we can set up a system of water sitting next to some surface, that hydrophilic surface that builds EC. And this water that sits next to it in the presence of a light, particularly infrared light, which is all around us all the time, uh, we can get electrical energy out of that. And so we get electrical energy from the environment. The sun needs doesn't need to shine. All that's needed is infrared energy, which is sort of not exactly the same, but roughly equivalent to heat.
Mhm.
Everything, if we were to turn off all the lights in your room so you couldn't see anything, and your video camera couldn't see anything, an infrared camera would pick up every book in your bookcase and all the writing on your t-shirt and et
Mhm.
cetera, et cetera. So everything is generating infrared energy. So from that infrared energy and water, we can get electrical energy. What remains to be tested is how much. We don't know how much, but conceivably, this could actually solve, um, possibly, we don't know, it needs to be tested, could solve our energy problem. So that's from a technological point of view. And so I see applications of easy water ranging from a health point of view to solving some of the problems of our environment. Also, we have a special filter that we build. You put contaminated water in, and it's set up in such a way that EZs build. And if you collect the EZ, all those contaminants will be out of the EZ and in the bulk water fraction, which you just dump. So, and we think it's possible, we haven't tested this extensively, is that one of the contaminants could be salt. So you put in salt water, like from the ocean, and you get out drinking water, um, and no energy is required except energy from the environment to do that. And right now, reverse osmosis is the way to do it, but the energy cost is enormous. So to summarize my long diatribe, the future, you asked me about the future, and I think the future ranges uh, from health all the way to technology, with many areas in between. It's, I must say, very exciting.
Sure sounds like it. Yeah, I agree, and I'm really looking forward to it all. And I'd love to make it to your water conference in Portugal. I've never been before, so I'm going to put that on the calendar, and hopefully I'll
Put
be
it on
there.
the calendar. It's a wonderful conference, a family-like atmosphere, um, where people having all the meals together, get to know everybody, and uh, really open discussions. It's a
I
great,
love it.
great, great place.
I love that. Yeah, like I mentioned at the beginning, water is one of my big passions. I stand for water and hydration to as many people as will listen to me. I love water fasting. I've had this water machine in my life for 13 years. So, yeah, it's a big area of passion of mine, and I've seen it help so many people. It's just so simple that it's just like, hey, everybody, hello. Why aren't we talking about this more? It's so, impactful and profound, but I'm really glad that I've had you on the show. Really grateful for you and all of your work and everything that you've done and continue to do. Anything else, the kind of parting words? I know we don't have too much more time. Anything else that's on your mind? I know there's so much more to it all, but any kind of final parting words or anything that people should kind of look into or explore or to think about here?
Yes, search for truth.
Mm,
Uh, Scientists used to be doing that. I think they're doing it less and less because the search for truth means taking risk. Um, but that's what science is all about. So those are my parting words.
yeah. Beautiful. I so agree. The truth will always come out, and I very much stand for that as well. So thank you so much again, Dr. Pollack. I really appreciate you, and until next time.
Okay, well, thanks for you, Adrian.
Of course.
Okay, take care.
Thank you. Thank you. Bye bye.